let's talk conditional probability. Okay. The probability of an event is often affected by the occurrence of other events and/or knowledge of information relevant to this event. Basically, by having conditions in the problem, it can modify the underlying sample space. This will in turn lead to changes in the probability of the event. As an example, we are in a presidential election year. Okay. The very first presidential primary occurs in the state of New Hampshire. In fact, it is written into their state constitution that they have to have their primary before anyone else. Okay, now, why do they do this? New Hampshire is a very small state. They have very few electoral votes. Normally, a presidential candidate would never visit a state with so few electoral votes. They'd go to California instead, or New York. Except for every presidential candidate always visits New Hampshire. Because they go first, there is a strong probability that whoever they vote for ends up being the actual nomination. Okay, so because they're first, their vote matters more, which is of course why they did it. Okay, let's do an example. You have a vase containing 5 black and 2 red balls. Okay, you're going to draw 2, okay, without replacement. This is important. It means I pick out one and then I pick out another without putting the first ball back in. If you put the first ball back in, it would change the situation a lot. So, what is the probability that my first ball is red? Okay, well, how many balls are there to choose from? 7, so that's my denominator. How many of them are red? 2, so that is my numerator. This is, by the way, about 28.5%. Now, what about if black is first? Okay, what is the probability that the second is red? So I have some extra information. So, of my 7 original balls, remember that I have already drawn out a black one. So there's only 6 balls left, 4 remaining black and the 2 red, and of those, 2 are red. This works out to be a probability of 33%. I just increased my odds, okay? This is known as conditional probability. Okay. This is the probability of an event occurring given that another event has already occurred. Okay. So, the probability of A given B. We write this as probability of A given that B has already happened. This is a little vertical line that is read as given. Okay. The formula for it, there's actually 2 versions, is you can do the probability of A and B divided by the probability of B, or you can do the number of things in the event A and B divided by the number of things in the event B. Okay. This can be rewritten to what is known as the product rule that says the probability of B times the probability of B given A, oops, I messed it up again, of A given B is the probability of A and B. Okay. All right. Let's do an example of calculating this. Okay. My experiment is to flip a coin 3 times. And I'm assuming it's a fair coin. Okay. So, without conditional, what is the probability that all 3 flips are heads? Well, there are 8 ways to flip the coin. 2 choices for the first flip, 2 for the next, 2 for the next. Multiply them and you get 8. Only one of those 8s is the outcome of heads, heads, heads. Okay. So, my probability is 1/8, or 12.5%. Now, what is the probability that I get 3 heads given that the first 2 are heads? Okay. All right. Most often, I'm going to use the second version of the conditional probability formula with the ends in it. Okay. And this is one time where sometimes it is easier to do numerator first. So on top, it's going to be the number of ways of satisfying both of these. Well, to satisfy 3 heads and first 2 are heads is really just to say, okay, I need 3 heads. Okay. Now, in the bottom, it's just satisfying the thing we knew had happened, so that's the first 2 are heads. Notice I will always write out this pseudo word formula version before I go near numbers. All right, so numerator, how many ways are there to get 3 heads? Exactly 1. We already counted that. Now here's the tricky part. How many ways are there to get the first 2 are heads? Remember though, my experiment is to flip a coin 3 times. You still have to flip it 3 times. Only I know the results of the first 2. They must be heads. So how many ways are there to complete this little diagram? That turns into how many ways are there to flip the coin for the third flip? And the answer is 2. Okay. Always remember that in that denominator, you still have to satisfy the overall experiment. Okay. All right, let's do another one. Okay. Our experiment is to roll 2 dice. Okay. I want to know what is the probability I roll an 11 given that the first one is a 5. Okay, so the formula says the bottom is number of ways that my first one is a 5. The top is the number of ways of satisfying both conditions. So if you have to roll an 11 and your first dice has to be a 5, okay, the only way to do this is to roll a 5 and then a 6. Okay. All right, so how many ways are there to get a 5 and then a 6? Well, exactly 1, because both dice results are prescribed. How many ways are there to have your first dice be a 5? Well, I have 2 dice. My first one is decided. There's only one answer. There's only one way to get a 5. But my second one still has 6 answers. So that is my probability, 1/6. Okay. Let's stick with the experiment of rolling 2 dice. And this time compute the probability of at least a 9, given that the first dice is a 5. All right, so on the bottom, it's again the number of ways that my first dice is a 5. On the top, okay, well, your first dice has to be a 5. What can your second dice be so that the sum is at least 9? Well, I could have a sum of 9, so a 5 and a 4. I could have a sum of 10, so a 5 and a 5. And I could have a sum of 11, so a 5 and a 6. Okay. I literally just listed out all the versions. There are 3 ways to do that. And still, the bottom, there are 6 ways for the first dice to be a 5, because essentially it's just choose how many ways there are of getting the second dice. Okay. All right. Okay. Let's go back to drawing 2 balls without replacement. I'm going to have 5 red and 6 blue balls, and I pick 2 without replacement. Okay. It has to be out without replacement for conditional probability to do anything. If it was with replacement, then I don't care what happened in the first draw. All the balls are back in the vase. Okay. I want to know what is the probability that the second ball is red given that the first ball is red. Okay. Well, according to the formula, on the bottom, this is the number of ways that the first ball is red. On the top, well, I have to satisfy both conditions, so the first one must be red and the second one must be red. Okay. Whew. All right, I'm going to do the top first. Okay, I have 2 balls to choose from, or to choose. How many choices are there for the first ball, given that it has to be red? Well, there are 5 red balls. How many choices are there for the second ball? Remember, I didn't put the ball I just picked out of the vase back in the vase. So now there are only 4. So 5 times 4 goes on top. For the bottom, I once again have a first and a second choice. The first ball needs to be red, so there are 5 choices for it. The second ball just needs to be a ball. Okay, so I don't care what color it is. It could be any of the 4 remaining blue balls, or red balls, or any of the 6 blue balls. 4 red plus 6 blue gives me a total of 10 balls. So 5 times 10, okay, this gives me 20 over 50, okay. By the way, generally with probability, I don't care if you simplify the fractions all that much, okay. You can write 2 over 5 if you want. Okay. All right. We are going to draw 2 cards from a standard poker deck. Okay. Now let's try without conditional first. What is the probability you draw a pair? Okay. All right. Well, denominator's easiest. So I have to pick 2 cards. How many choices are there for the first card? Well, 52. That's how many cards are in the deck. Once I have picked the first card, how many choices are there for the second? 51. Okay. Now, in the top, I need to draw a pair. Notice, however, I didn't say what type of pair. A pair of aces, a pair of jacks, a pair of 2s. So I need to know what type of pair before I can actually go picking my cards. Okay. There are 13 different types of pairs, 1 for each rank. So first I will choose what type of pair I get. Once I've decided, say it's jacks, there are 4 jacks in the deck, so there's 4 choices for my first jack, and once that is chosen, there are 3 choices for my second jack. Okay. By the way, 13 times 4 is 52, so I can kind of just cancel those right off and say this probability is 3 out of 51. Now let's do a conditional. What is the probability I draw a pair given that my first card is an ace? Okay. All right. So on the bottom, I need to count the number of ways of drawing 2 cards where my first is an ace. On the top, I need to count the number of ways of satisfying both conditions. Well, if your first card is an ace and you have to draw a pair, you need to draw 2 aces. Okay. All right. So how many ways are there to draw 2 aces? Well, there's 4 choices for the first ace and 3 for the second. How many ways are there to satisfy the bottom? Well, my first card needs to be an ace. There are 4 choices. My second card can be anything except for the card that's already been drawn. So if we start with 52 cards and we've drawn 1, I now have 51 cards as an option. Okay. This gives me 3 out of 51. Okay. Why is it the same? Well, that's one thing that makes cards very interesting. Okay. Whew. Now, 2 events, E and F, are independent if the probability of E does not depend on whether or not F happened. Okay. Another way of saying this is that the probability of E given F is just the probability of E, because I don't care if F has happened, and the probability of F given E is just the probability of F, because I don't care if E has happened. Only when we have independence, then you can use the following shortcut for computing the probability of E and F. It is the probability of E times the probability of F. Okay. So here's the problem, though. You're assuming things are independent a lot of times when they are not. Okay. So basically only use this when you're flat out told that things are independent and you trust the source of that information. It has led to numerous cases of people being wrongfully convicted because juries get really confused by math And lawyers are really good at making people think they know what they're talking about. Okay. So, let me give you an example of when things are independent. Okay. I'm going to draw one card from a poker deck. I want the probability that it is red and a queen. Now, I could do this the normal way, except for I claim these are independent. Whether or not his card is red has nothing to do with whether or not a card is a queen. Okay? There's not more red queens than black queens. There's not more queens that are one color or the other at all. They're totally independent properties. Okay? So, by the above statement, this is the probability that a card is red times the probability that a card is a queen. All right, well, half of the deck is red, okay, and there are one queen for each 13 cards, because 1 out of 13 is how many ranks I have. So this gives me a probability of 1 out of 26. Okay. So, let's apply this to a crime scene. Okay. Suppose, well, actually, this is a true statement. Only 1.5% of the population of the world has a blood type of B negative. Okay. Okay, so this is a known fact. Now we're going to suppose blood from an attacker is B negative. Okay. There are the suspect pool consists of 200 people. Okay. So what I want is what is the probability a person is innocent given that they have B negative blood? Okay. This is essentially saying why it is a bad idea to use this B negative blood to narrow down suspects, even though 1.5% seems awesome, right? People assume that means that 98.5% of the time we're going to be right, and they're accepting of that probability, but that is not, okay? So, again, if we use the blood to convict someone, okay, this would be the probability that we wrongly convicted them. Okay. All right, according to the conditional probability formula, on the bottom, we count the number of people that are B negative. Okay. On the top, we count the number of people that satisfy both of these, that are innocent and B negative. Okay. All right. So let's go off to the side. There are 200 suspects. 1.5% of them we will assume to be B negative. To find 1.5% of 200, we multiply 200 by 0.015 because we turned the percent into a decimal. This equals 3. This means there are 3 people in our suspect pool that have B negative blood. Now, because of this statement, one of those is guilty. But that means that 2 of those people are innocent with B negative out of the total 3 people that have B negative blood. This is a 67% probability that we have the wrong person. That's really bad. And this is why you have to be careful about conditional probability. Okay. All right. That is the end of our lecture for today. I'll remind you of a couple things. Okay. A lot of you are missing a very large amount of homework. The case study is also up that is due at the end of the semester. Okay, it's a good idea to work on it now because you're also going to have a take-home exam at the end of the semester to work on. As always, I'll be on Zoom if you have questions. Have a